Okay, so I don't actually watch Jimmy's lectures, but I load them up and I click the skip 10 seconds thing all the way through it. And so there was some question on why I stream. And the reason is because the old laptop I have in my office, forgot the word for office, it could either record or stream, but not both. And it also took a really long time to upload videos. So I just started streaming only. Then I had one case of a student saying, wow, I had a really rough day and it was like hard to get out of bed, but I could watch the lecture while it was happening because it was streamed instead of recorded and posted later. So like I didn't get behind on things. I didn't have to like wait 3 hours for the lecture to be uploaded. So that's why I stream. There was some allegations that I don't check stream chat, but I also ignore all of you in the room here with me while I'm teaching. So like that's the exact same level of interactivity. Am I proud of that? No, I just pretty much the only person I interact with while I'm giving my lecture is like my inner demons, and we just that's the noise they make. Yeah, so Jimmy showed you a solution to malloc that is like, well, to the getter and the setter, which is like, I don't know, like those all could have been on their own lines in different expressions, right? And then it would have been, and then there wouldn't have been a turbofish, and then there wouldn't have been, okay, yeah.
I have a question.
Yeah.
You keep saying turbofish and talking about turbofish, and I still don't.
Oh, yeah. Yeah, so the turbofish. It's this thing. And so, well, I think the good example was transmute. Let's pull up transmute and look at that. Transmute. Okay. So, I posted my solutions to transmute as well, right? Or I think so. I think this will work. Okay. So, what does the turbofish do? Great question. Good question. I don't even know if I taught this last semester or not. Was anyone who was here last semester? I think I explicitly didn't teach the turbofish because I hate it. Does that sound right? Okay. I still hate it. It's not my fault that it's bad and wrong and evil. Okay, so this is one way to take a U32 and use transmute to turn it into an F32. In this case, I'm actually doing arrays. And then I can look at the outcome, and I think this is nominally 0 or something. Let's see if this is correct. Oh, it's 1. Okay, so what's going on here? I'm taking variables of known type, and I'm transmuting them into each other. Now, I don't actually have to label the types of these variables, I don't think. Let's see, I'm not super up to date on the Rust annotation. So I can get rid of these things, which are like sort of annotational niceties, right? Okay. And if I do that, and then I try and cargo run, it won't work because there's typing ambiguity, but I can specify the types in one other place. I don't have to specify the types at the location of a variable because I don't actually have to always put variables anywhere in particular. For example, I can grab this value and I can place it here. And I think this is like equally problematic or something. I'm used to doing build. Okay. Oh yeah, there's a semicolon in there. Whatever. But there's another place I can say what type something is. I can go after the function name, and then I can use the like 2 colons, which is Rusty's for like look inside this thing, and then I'm going to specify the type inside these brackets. And Twitter user Garblefart said this looks like a turbofish. So everyone started calling it a turbofish. I think it was first on Twitter and then on Reddit. And so I think like these are fins, and this is the fish body. So it was like never intended to be called the turbofish. Someone on the internet called it that, and it stuck. Okay, and then I think this is going from an and U32, so a reference to an array of U32s, which is what this is. And we're going to transmute that to a reference to an array of, I think it was F32s. Is this going to work? Wow, that actually worked. That's crazy. First try, too. This is why you don't need a language server. So whoever tells you you have a language server, I've never written that code before in my life, and I don't know what it does, and I got it on the first try. That's how easy Rust is. Look at this. That is apparently Rust. That does look like Rust to me. Okay, so there's another thing that my haters want me to do. I don't actually know which haters. So some people think it's weird to write this whole thing out every time. And I think you can say use std mem. Can I put transmute here too?
Yeah.
No, I can't because I don't remember how to spell it. So that looks right.
Yeah.
Okay, and then you can do that.
Yes.
Carg run. Okay. Okay, and then obviously, like, you all know I have opinions about code, right? You figured that out about me.
Unfortunately, yeah.
Using variables is bad. So we're gonna get rid of the variables here. I still don't know how the Vim cursor works. That's why I keep getting one letter off. Okay. And I know what you're thinking. You're thinking this might work. Not quite, actually. This thing's an array, so we have to look at the 0th element in it. I bet this will work. Wait, no. Oh, shoot. I forgot Indy's here. Cargo R. Okay, it's fine. Yeah.
Isn't the compiler just going to undo that?
Undo what?
Like, not having any variables?
Oh, no. Yeah, so the variables aren't bad for the compiler. They're bad for us.
Oh.
So so when you use variables in your code, it prevents you from building character, right? So I don't actually know when in my life I started trying to write code without variables in it, but I can't stop now, right? Like I've committed.
It's addictive. It's addictive.
It's incredible how much serotonin you get when you get the last variable out of your program. It's like, kids, you don't need to do drugs. Trust me. Like, drugs are like pretty cool or whatever. They also cost money. Okay, first of all, like, let's be real. Which I guess won't be a problem for you now that you know Rust. Anyways, I still think this is cringe. So.
For some reason with transmute, I tend to use the import less often than just standard vim transmute. If I'm like writing my own code or like have my own libraries that I'm using, I'll import the libraries, but I do it a lot less for things in standard vim for some reason.
I think it just feels good to type out, but I've done the same thing.
I feel like by the time you're writing Rust, you should be maximizing the number of characters on the screen. Just like the more you type, the better, right? That's how I feel about Rust. So anyways, here's a completely reasonable way to do things. Should we do anything else with this? I guess this was basically my solution to whatever that thing was that we did. A homework. No. Yes, the transmute lab, right? Yeah. Okay. So this is the turbofish. And why is the turbofish bad? I just think it's ugly. So, like, the thing that I've been dealing with in my life is, do I hate the turbofish more than I hate variables? And so far, the turbofish has been the greater object of my ire. Yeah, okay. There you go. I think the saying is something like, fish that is turbo, good language, faux show, fish that is, I don't know. That's as far as I got. Okay. I love malloc. I like malloc so much. I like malloc in C. I like malloc in C so much, I just made you write malloc in Rust. Malloc's awesome. If you're not having a good time with malloc, that sounds like a you problem to me. If you're looking for a challenge problem in malloc, implement your own linked list in it using 8-bit pointers, because there's not that many pointer locations, and then write merge sort in malloc. And it'll be awesome. And then the other thing you can do is you can implement a subtraction linked list and then block move it. So, okay. I was like, malloc's hard. I should be nice this week. And I think I was. So I think the homework's not going to be brutal this week. But I was going through these slides while I was making them, and it seems kind of hard. Maybe like tedious. There's like a lot of things going on. And there's a lot of stuff from like other areas of computer science and allied fields that are bubbling up a little bit. I think one of your TAs can't figure out why I'm not teaching assembly or threads or something. I've been trying to contain assembly to another possible class, which is the compilers class, which I would presumably teach next year. So I've been not going into assembly too much, but we're getting to look at some stuff that looks an awful lot like compilers stuff, because we're making a freestanding binary, which means you can't make certain assumptions about the underlying system. So there's some topics I was hoping to isolate that there's sort of just like no great way to isolate, and they're going to come up today. Anyways, and today's class is called Bare Metal, which is probably the sickest class name we're ever going to have for a lecture anywhere in this program. I'm sorry. It's just, that's as good as it can get. I am stealing everything. I'm stealing without shame. These are stolen from a blogger and from Google. I got them working. I made some changes. I Calvinified them a little bit, which probably you think made them worse, but I think it made them better. But I'm also going to provide some motivation before we get into it. Okay, so today is my favorite day of the week. It's Throwback Monday, and I was going to, just call out some stuff that's happened historically. So this here is a blog post from Ray, and I was the second person to graduate from my advisor's research group, and Ray was the first person, so Ray's the smart version of me, which was really good for the old self-esteem while I was in grad school. But anyways, Ray got a master's in double E before going to grad school in computer science, so I showed up kind of knowing low-level C, thinking I was pretty smart, and then Ray was much, much better than me at everything. So anyways, in February 19th, 2016, when Ray got tired of talking to me in real life, she wrote up this guide that explains, I try to make everything as simple as possible. That's at me. That's directly at me. Anyways, here is just a description of something that we did in grad school, where we had a hardware design, which was the OR1200, which stands for Open RISC 1200. RISC stands for Reduced Instruction Set Computer. It is a type of architecture. It is a type of architecture that competes with x86 64. RISC lost, but it's still around a little bit. The benefit of OR1200 is the O. It's open source, so it's a free and open source hardware architecture that we were able to use. Now, did we actually have a physical chip for this? No, we're academics. We don't have money, right? So what we actually had is we had a computer program that was pretending to be an open source hardware. And this, in 2016, was how we wrote READMEs, because this is not in Markdown, is it? This is a Medium article. So however this is specified, I don't know. So this is not a Markdown code block, because I think people weren't using Markdown yet then. Blah, blah, blah. You create something, I don't know. This is a Open RISC processor system on a chip version 2 simulated. There's some really nice olives.
Cherries, I think.
Cherries?
Cherries.
Those are cherries?
Cherries.
Did you red for olives?
Definitely.
I guess olives can be red, but not like that.
Yeah, not that
I'm pretty
much.
sure those are cherries, yeah.
What's in the middle?
You could have let me have one thing.
Well, that one thing is just cherries.
Okay, I'm going to say what I think this is, okay? That's a pear?
Apple.
Okay.
Apple, that could do hair, I think it's.
Okay, these are craisins.
Yeah.
Okay,
Those are petals of some kind.
this stuff here,
It's like tea.
Yeah.
I'm going to say open source hardware. Okay.
I agree. Yep. There's no other explanation.
Okay. Anyways, I suspect you can still follow this guide today. For example, here's C Hello World. And what is this? This is our good old friend GCC. So we use a specific version of the GCC toolchain to compile this helloworld.c program, and we compile it into an ELF file. I think ELF files have come up a few times. That's executable link format, which is one of the old executable formats used on Linux and still used today. We can create an assembly listing, which is the level of programming below Rust and C. We can convert it to a binary, and today we're dealing with binaries. And then, what's this step? This is the kind of sketchy step. This is getting a little goofy. We turned it into a virtual memory file. And the virtual memory file can be read by a virtual machine, which treats that memory as if it contains no memory contents other than the executable to print hello world, which is pretty cool. Then what you do, then you simulate it. You take the virtual mem device. Somehow this runs, I don't know. And then you produce a value change dump file. If you succeed, you will see Hello World on the screen several seconds after running. What? Several seconds? Right, yeah, this takes forever because your computer is going to imagine a fake computer, and then that fake computer is going to imagine turning on. So this is slow. This is not fast. One time, I tried to boot Linux on one of these things while logging it. And it ran for 16 hours, and it crashed when it filled my hard drive with logs. And it didn't do anything. It ran for like a couple clock cycles or something, right? And that was awesome. Like that, I've never like filled my hard drive before, so that was really fun. Like a terabyte or two, I don't know, something. Yeah, and I was writing down the values inside computer registers in binary ASCII, so it was not efficient. Yeah, this is cool. And then I'm going to name some of these things. Pair. Right? These over here.
Those are red.
Those are diesel engines.
Those are red. Reverse of red.
This stuff in the middle. Oh, I had one, and then someone said granola. Sawdust, right? Right. It looks like stuff that comes out of a wood chipper. And this over here, that's motor oil, and it has a pH test strip in it. Okay. Okay, so then I came to Willamette University at some point in time. Do any of you know Junie? Or is that too much of a throwback?
Yeah.
Yeah. So I mind controlled Junie into doing some of my research for me, using a clever trick known as compensation, which is what I plan to use on some of you this summer if you don't look out. And Junie was like, why don't you research? Undergraduates like doing research in the summer. They don't like getting jobs that I'm not responsible for. They always want me to find them a job, right? You all understand this, right? Yeah. Okay, so anyways, so Junie did this with RISC-V, which is the new open source hardware. And this was a little cool. You can sort of click through here. And I guess this was all dispatched from QEMU inside of Python or something. But Junie was actually handwriting a hex file, which was pretty cool. So if you want to, okay, no, it wasn't handwritten. Apparently, it was. Maybe it was. Oh yeah, this is regex reading the output. Okay, cool. So anyways, I linked to this research talk. You can look at it. I don't have a recording. It's a cool one.
It's just the research talk. I was there for when Junie presented at SSRD.
Oh, okay. Also. I gave a talk recently at the Pacific Northwest Software Quality Conference, where probably some of you should present a paper with me next year. The call for papers just got posted, so like, if you're going to be around for another year, let me know. Maybe you'll get a job. I don't know. They're all like test engineers, though, which like some people, like that's not narcissistic enough for them. You'd be testing other people's code. And they don't seem to be as into free and open source software as I am. But anyways, I went to this software quality conference, so of course I gave a talk on hardware quality. But what I cheated. I simulated the hardware and software, so it's okay. this is another example of bare metal. And what is this? I actually wrote something that I could solder onto a board. And then I wrote a series of hardware signals that would exercise the design. And then I simulated the design and created, once again, a value change dump. And it looked like this. And everyone was really impressed with this. So I just want you to know that everyone found that impressive.
I know one of those lines.
Which one?
Spell resetting with one T.
Where?
That one.
Resetting? That's supposed to have 2 T's?
Yeah.
Yeah. Reset change. So if you open Vim and type in set spell, it'll highlight words that are spelled wrong.
Wait, will. No.
I don't like the internet anymore. Yeah, I don't know. I think I can admit when I'm wrong. I do think that. It's true that I think that. Okay. All right. So what's bare metal? I don't know that this definition really makes sense. It seems like some of the things that are described as bare metal these days have something awfully close to an operating system running on them, like they've got a ton of libraries or something. Every once in a while, I see something that says, like, hey, I wrote Hello World bare metal, like Ray's example. And, like, I don't know that you did, because it seems like if there's any way for it to display anything at all, there's something that's an awful lot like an operating system in between you and the code. So, whatever. I think people sometimes say bare metal when they don't quite mean bare metal. I think a lot of times they mean embedded, so they mean not on a, I don't know, a commercial PC or something. But anyways, in theory, in the olden days, back in the dawn of time when people said bare metal, really what they meant is running on hardware with no underlying operating system. It shouldn't be that surprising that we can do this. We imagine the von Neumann architecture, where we have a CPU and MMU. We imagine writing a series of assembly instructions directly at address 0 in the memory accessed by the MMU. We power on the device. It queries the MMU for the first instruction, reads it directly from memory, and can begin executing commands or assembly instructions or whatever you want without there being any operating system present. Of course we can do this. It's simply not always interesting. Bare metal, I think, is the only way that this is referred to. It does show up in job postings. A lot of the bare metal job postings right now are for, let's see if I remember this, cloud engineers who are writing drivers or scripts or something that are running on Internet of Things, like edge computing devices, so like sensors that exist in the world or something. And you write highly optimized code on these things because you want them to be very low energy. And they exist like off the grid somewhere, and then some data pipeline conveys some bits out of them every so often and like puts it in a data lake somewhere. I don't know. That seems to be where people are writing bare metal right now. I thought a lot of people in automotive and aerospace were also writing bare metal. Looks like a lot of that stuff to me. There's now real-time operating systems in between you and the metal in almost all cases. So I think bare metal is pretty much only Internet of Things now. I don't know if that's true. That said, if you are working in the real-time operating system space in automotive or aeronautical, you're probably going to want to know how to write bare metal code anyways, because it's going to be much closer to the code you write than the conventional code. I'm going to introduce some terms. These are not, they're not really operating system terms, but I guess like some of them also aren't really not operating system terms. The words I'm going to have to say at various points in time, and you should know what they are in case you see them around. So this is like a bit of a digression, but I think it's a necessary digression. The terms are simulation, emulation, cross-compilation, and QEMU. Okay, so I said when Ray was running the OR 1200 open source design, we didn't have the actual physical hardware. So what did we do? Well, there's two things you can do. You can focus on determining what OR 1200 would do, given some series of inputs, what outputs would it produce? That's the only thing you care about. You model the hardware as a black box. Some ways you can model hardware as a black box is, for example, you can say, oh, we have a design specification that describes what happens under certain conditions. So we only are concerned about high-level results. We're concerned about what goes into the hardware and what comes out of the hardware. Simulation is used sometimes nominally for performance or logic testing. I have not seen simulation in use in years. It was still in use in 2015 when we were playing around with it and looking at different options. It's a little bit too far removed from actually studying hardware to often be useful in practice. So I don't see a lot of simulation around. But it's possible, and it's not that bad. And you all have done an example of this because the F16 lab in Systems in Rust was basically hardware simulation. We were not actually modeling having a floating point unit, but we were writing in software what a floating point unit would do. Simulation is nominally faster but less precise. Neither of those things are true anymore. Emulation is a little more popular. And what's the difference between emulation? I'm no longer just looking at the inputs and outputs to some theoretical computing device. Instead, I am writing code that simulates all of the internal workings of the computing device. So, if my device has 32 registers, I have variables that represent each of those 32 registers. And I emulate the values in each of those 32 registers, regardless of whether the values in those 32 registers are visible to the outside world. One of the reasons to do this is, at least in the most advanced modern designs, there are registers that do not look like they should be visible to the outside world, that still have behavioral effects that become visible to the outside world. So there is difference in performance between the expected simulation results and the actual emulation results. And virtually all of these things were security issues. So the software acts as hardware. It has a programmer script that models the CPU. It has a programmer script that models registers. It has a programmer script that models the MMU. I think, am I going to say this? This is a crazy thing to say. I was going to say this. This is actually a reasonable application for object-oriented computing because you're simulating physical objects. So you can actually make a class that represents one of your CPU cores. Have I ever done this? No, out of pure spite, I don't use any of the object-oriented features of any of the simulation and emulation languages. But if I find out after you graduate here that you've been using object-oriented notation for this, I will not be as mad as I would be if I found out you were doing it to use like data science or something, right? I saw someone using object-oriented notation for a neural network the other day. No, they're matrices, okay? Right, okay, so accuracy to speed. In the olden days, what we said, emulation is infeasible. It's too computationally expensive. If you turn it on, you'll fill your 1 terabyte hard drive with ASCII, which I did. And that turned out to be kind of fake because a lot of the devices people were emulating were either equivalent to or simpler than the devices they were emulating them on. So what they started doing is just running the code directly on the host device with logging turned on, and it was exactly as fast as running it on actual physical hardware. So if I emulate x86 on x86, I pay a very, very low overhead cost. The only thing I'm paying basically is the logging cost, and logging is expensive no matter what. I want to talk a little bit about this idea of a goal, which is that if I create a piece of software, and in this case we can think of it as a freestanding binary. I create some binary, and I want to run it on emulated hardware. I'm not using the term emulate the binary, because that's not really what I'm emulating. I'm emulating the hardware that is running the binary. So I have some description of a hardware design that I feed into an emulator, and then I additionally furnish the binary. Guest software doesn't know it's not on actual silicon. There should be no query or operation or any action that can be taken by that freestanding binary such that the behavior of the binary differs from if it were running on actual physical hardware. So from the perspective of the software running in emulation, everything should appear identical. Now, what are some things that might not appear identical? Well, if I'm running on emulated hardware, I might be emulating hardware that has, for example, some assembly instructions that my host machine doesn't have. For example, I think we wrote the Hamming weight and Hamming distance operations in a previous class. So maybe there's some relatively complicated bit operation I'm using inside of a cryptography core or something like that that isn't actually implemented on my host system. So when I'm emulating, I'm going along and it's like, oh, I can add things together, no problem. I can subtract things, no problem. I can do logical OR, no problem. Whoa, what's this bitwise operation? And the host machine will have to stop, switch out of hardware, and use a software implementation of that bit operation, and then update the software idea of CPU, registers, memory, and so on to have that value in it. However, the executable that is being simulated doesn't have a notion of time, because the only way executables can tell time is they can query the underlying system and ask for a timestamp. So the executable that is being run on top of the emulated hardware won't notice that the emulator is doing an expensive operation or taking time to figure out some bits. So the output behavior, or anything that the sort of binary running on emulated hardware detects, will appear identical to if it's running on hardware. And so this is the measure of maturity of emulation. If emulation is indistinguishable from running on actual hardware, then it is successful emulation. Here's the closest thing that I could come up to with for an example. My understanding is x86-64, which this device is running, is the Intel AMD. Should I put AMD first there? It's also called AMD 64. It's common for Linux and Windows, and it supports nominally, I don't know, I've never used it, a long double float with 80 bits of precision. I don't know when you need 80 bits of precision for your floats. I've never used these. Well, I don't use floats at all. And I guess Apple came along and noticed no one ever uses them at all and just wrote them out of their version of ARM64 they're using for Apple Silicon, so the M1 processor. So we have a variety of Apples floating around this room, and none of them have 80-bit precision floats on them. However, maybe somewhere out there there's some executable that's written for my Intel device that relies on an 80-bit float for something.
The reason it says that isn't because floats are is because it uses it as for more accuracy during operations, but they're still reported as 64-bit in registers.
So it's an internal.
Yes.
Oh, but okay. So then that means if you do a float calculation on Intel, it might come back more accurate. So you would still perceive there's a different internal.
Yes.
Okay. And so somehow, Apple Silicon has to detect that that might happen and have an intermediate emulation layer that performs some slower unpacked bit algorithm, arithmetic, over these 80 bits and get the correct answer if it is emulating an x86 piece of software. I'm assuming there's at least one video game that does this for some sort of internal calculation, so maybe that's like gaming on Mac or something. I'm assuming you're not hitting this in machine learning anywhere, because I think they use relatively low precision. So I don't know. But ARM64 is supposed to have a pretty good emulation layer. I believe it's called Rosetta. And that Rosetta emulation layer has to deal with this problem. I claim it is trivial to implement a float in software. It's so easy, in fact, you're not going to believe this. I tricked undergraduates into doing this just last semester.
But it was really hard, though.
Was it hard?
Yeah.
What part of this was hard?
You didn't explain what floats are very well.
So we're blaming me for it being hard? Are you sure I wasn't just building character? Did I really not explain floats?
Not very well.
This kind of looks like I'm explaining things well. This looks really good to me. I think perhaps the problem is I explained it exactly the way I wanted to learn it. Okay. Your feedback is noted. Okay. It is relatively... Okay, so yes, I claim it's trivial to implement a float in software. Apparently not if I teach the class. Then it's hard, right? Whatever. You're welcome. Okay, and so I do claim it is relatively non-trivial to implement an architecture in software though it's definitely possible. Here's an example. Let's just look at this quickly. This is Pico RV32. To my knowledge, this is the smallest RISC core. It is size optimized. A lot of stuff in here. We probably don't need all of this. Actually, do I have a... I think I have a better version of this. Hold on. I forked this. No. Is it just called Pico? I'm gonna find this. I'm smart and valid and worthy and good and not at all flailing. I'm flailing. I don't know what I'm doing. I'm losing my mind. Wait, no, it's under a different thing. I'm gonna find this.
Is it on the League of Legends or Reddit?
It's not on the League of Legends Reddit. Okay, first of all, I only check that like a couple times a day. Well, I mean, presumably you've all been following Los Ratones playing against the LEC teams, right?
You could presume that.
I do. Okay. So anyways, here's a hardware design. This has nothing to do with the League of Legends subreddit. I only go to like 3 subreddits, okay? And none of them are involved in cybercrimes. Write that down. Is that right? Okay. So this is the Pico RV32. That's a .v file. It stands for Verilog. Let's see. This is 3,000 lines of code. Not that bad. I think like a human could look at this and understand it. But just for like some sense of what we're looking at here, if we emulate this, or these are parameters. We don't care about those. I have registers. Some of them are inputs. Some of them are outputs. They have different names. Some of them are big. This is 32 bits. This is a memory address. So this is a 32-bit processor, so its memories are 32 bits. Got a bunch of these. I don't know. There's like 100 registers or something. That's not right. There's around 300 registers. I just know because I checked. But you can also just... That's probably not what I want. There are... How do you count how many instances of something there are in a computer? Anyways, this is what some hardware looks like. And then after you finish sort of declaring all of your registers and wires and stuff, then you begin to start copying values across between different registers in response to different events and so on. And then at some point in time, finally, you have... Ooh, we have like different flags being set and so on. So 3,000 lines of code, I think, is within the range of probably an undergraduate project. So I think like if I had you for a year, I could make you write a RISC-V processor. I don't think I could make you do it in a semester. So that's about how hard I think this is. Simulating, it's pretty easy. You can do this. Okay, that's emulation. Introducing another term. This term is cross-compiling. Hopefully at this point in time you know what compiling is, but I'll say it again anyways. Okay, I've written source code that's human readable. I have an executable that takes that human readable source code and produces a machine readable executable. Now, oftentimes when we do this, we create the machine readable executable for the machine that is performing the compilation. So if I have an x86 machine, I compile and I get an x86 binary. If we are cross-compiling, you do not necessarily do that. One of the examples of cross-compiling is sort of the thing that I showed you earlier that Ray did, where on our x86 research machines, we cross-compiled to create an OR1200 binary. So it referred to different registers and it used different assembly instructions. I understand this to be pretty common in embedded applications. As a rule, when I see someone working with like a board, like an Arduino or one of those things, they plug it into their real computer with some sort of wire, and then they write code on the real computer, and then they press a button, and the code goes from the real computer into the tiny fake computer. And oftentimes, in between those two steps, there's a compilation step that happens on the big computer, right? I just can't get this example out of my mind, so I'm going to tell it to you because I think it's easy to think about. So there's thermostats, right? Many of them are made by Honeywell, which is like a big semiconductor company. So thermostats have processors in them. And I'm assuming they don't run compilers on those processors. But I'm also assuming those Honeywell thermostats are running code. So someone wrote that code somewhere, and I don't think they hand wrote it in assembly. I think they cross-compiled it from an x86 host device, just like this one, and then they loaded it on to processors, and maybe they put it in read-only memory or something. I don't know what they did. But someone at some point probably wrote code on a device other than the device that code is running on. And I think a thermostat's a good example of that. Maybe this projector is too. Maybe the projector code was cross-compiled. Trying to avoid namespace collisions, compiler runs on host A, produces a binary for target B. Where you compile and where you execute are different places. Very common for bare metal development. Why? You're probably not going to be able to run a compiler in bare metal. That sounds really hard. You definitely could try that. Oh, right, and this stuff goes over a wire. It transmits over a wire. If it goes over something other than a wire, you're going to really wish you had an operating system. Why is that? Because it's coming in over the bus, right? And so if this is coming in over the network, it's having to go through a network card. What's dealing with the network card? Your operating system, right? So for bare metal, you probably want to just be throwing this over a wire directly into some memory on whatever your target device is, and then your target device will read from that memory and execute. Has anyone in here cross-compiled before for any reason? Okay. So it's a real thing that happens. I don't know how often it happens. I've done it a bunch, but it's like my research area. Okay, when you're cross-compiling, you must target a specific architecture. So, for example, OR1200, for example, RISC-V, for example, ARM64, for example, x86. And then you must link against specific hardware memory maps. I'm hand-waving linking for today. I think we're dealing with linking in the lab. I was like looking at how hard this content looked. Oh my, I've been talking for like 10 years or something today already, right? And we're on slide 14, right? So I didn't want to rush this content, but anyways. So you target a specific architecture, you link against where its memory locations are. Why do you do that? So maybe one way you're writing hello world is you're going to blink an LED in Morse code or something, right? So somehow you have to know where the LED is. And somehow you also need actual hardware unless you're either a cheapskate or a genius, and you get to choose which one. How much text did I cut off? That's not that bad. Okay, so QEMU, 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 we don't know how to say it. It's this thing, it's this little critter right here. The QEMU that looks like an emu. This thing's cool. I think probably some real company somewhere is just like throwing money at these people. AWS, they're funded by AWS. That's a lot of money. There's this place called Oregon State. Never really heard of them. Oregon State?
Yeah. The penitentiary.
That's
Curiously close to being true. Okay.
There's a place called Oregon State Penitentiary.
Yes.
You could say schools have like presidents who do for code there, but that's not what I was going for.
Yeah, I mean, I wasn't going to say that, so it's just interesting it came up. I was reading this very interesting study on the impacts of going to school every day on your mental health. And
Pretty bad.
yeah, it's crazy bad. I almost decided to drop out, and then I realized I'm not in school anymore. Okay.
Go to a school.
It's kind of weird that I'm like super old and still in school. And I've like never been anywhere else. I had a real job for like 4 months. Speaking of things that aren't real, QEMU, the emulator. Because I don't have a real job, I don't have real money, so I can't buy real hardware. But software is free, right? So I used QEMU to pretend I have hardware. It supports both emulation and virtualization. Virtualization, basically, out of scope. You emulate the entire device rather than just the device executing the binary. It's not that complicated. Very common in cloud. Very fast now, very secure now, getting faster and more secure every year. Huge topic. Actually, I guess the Jimmy Cloudflare runners, that's probably some virtualization technology somehow, right? I don't know.
The workers primarily actually run V8 combined with WebAssembly.
Okay. Do I think WebAssembly is virtualization? Probably not. Okay. Okay. So this lets us run bare metal binaries without physical chips. It would have cost me about $600 to get all of you physical chips this term. And that's 2 pairs of Nike Alpha Flies that I could have bought instead. So, sorry. Maybe you should have picked a teacher that cares about you more. And so the way we're going to use this is we're going to write code locally. We're going to cross-compile it. But we're going to keep the cross-compiled code locally. And then we're also going to locally run QEMU. And we're going to provide the QEMU instance with the cross-compiled code. And the QEMU instance is going to simulate the hardware, simulating the software. And then we'll get our outputs, such as they are. And I think that's the homework this week. I'm not sure. I'm going to see how far we get in class today. Okay. All right, binary. Everyone's favorite number system. It is so annoying to me that binary is used as a term for executables. That's just it. That's not what it means. Everything in a computer is in binary. Okay. They should have called it like machine code. Like bare metal sounds cool, right? The only problem with it being called bare metal is what does it run on? Silicon, which isn't a metal, it's a metalloid. So they should call it bare metalloid, right?
It's a band name. You used to spell bear the other way.
Spell it the other way?
Like the creature.
BEAR metal.
Oh, like RAR. Yeah.
That's kind of cool.
We can call it like grizzly bear metal. I see. Okay. Yeah, I'm locked in. Okay. So, operating systems. What we're all here for. Should we like let out a quick like whoop whoop for operating systems? Maybe get the energy back a little bit. Okay. I'll count us off, and on 3, I will whoop, and you can join or not. Okay. This is going to be a whoop whoop for operating systems. 1, 2, 3, whoop whoop. Okay, there was really good participation there. I appreciate the energy. We're too far behind to have time for monkey type, so we gotta get our kicks in where we can. Okay. The first step in creating an OS. Well, first you create the OS kernel, which is the part of the OS that interacts with hardware. We've got to create a binary that doesn't link against the standard library, because the standard library assumes an underlying operating system. Okay. What does link mean? Well, we sort of hand-waved link earlier, but basically most of the executables we write, they know where in memory they can go to ask for print. They know where they can go in memory to ask for file open. So we need to not be able to do all of that stuff because that needs to be provided by us. So somehow we need to be able to run Rust code on bare metal without an underlying operating system. Now you can actually just do this even if you have an operating system if you just happen to not rely on it. You just have to know you're not doing that somehow. Okay, so we're basically dealing with this big recursive problem where most written code assumes an underlying OS. We're trying to write code that is an OS, so we can't assume our own OS. So some things we can't use. Files, that one makes sense, right? Files are complicated. The heap, ooh, I was kind of hoping I'd get the heap, right? But in fact, you all are allowed to use the heap now because you wrote your own malloc, so you can use that if you want. Networks, definitely against the law. Unless, of course, you write your own network, right? Random numbers, totally banned. Remember how we did random numbers? You all love random numbers, right? Remember this thing? Yeah, so that's part of the operating system. So that you don't have that anymore, okay?
How hard is it?
Pretty hard?
Randomness is kind of hard.
Yeah. You can make things that seem random pretty easily.
I'm pretty sure that's what random is. Yeah, unless you have like some kind of like hardware-assisted randomness that's just used for cryptography stuff, it's hard to like get.
Hear me out. This is different every time. I bet it's random.
Will you know what happens different every time, and then when it goes up by 1 each time?
Okay. So, yeah, we had a brilliant idea. From itertools import count, right? We'll say r equals count, okay, and then we'll say, wait, oh, it's different every time. This must be random.
It could be random.
It could be random. We're so lucky. Okay. Okay. I think I've said some of this before. We can't use all of the Rust standard library, but the stuff we can't use is the portion of Rust that relies on an operating system, so it's not things like language features. Like, it's not like we lost access to variables, which, to be clear, would be awesome. But that's not what happened. We still have variables. So you're still allowed to use variables. You're welcome. I tried to design this class so you couldn't use variables, and I couldn't figure out how to do it, right? And you keep some pretty cool stuff. So in other lesser programming languages, there's something called the for loop. It's in Rust too, but it's also in the lesser programming languages. But there's also still iterators. There's closures, which I don't think we use at all. Jimmy, have you taught them closures for any reason?
Yeah.
Did they use them?
Not really.
So you taught it for no reason. Okay, that's fine. No, I teach things for no reason too. Pattern matching, which is awesome. Okay. And then there's option and result. And I would like to reiterate the official Calvin Deutsch-Spine position on option and result. That's why Rust is good. Do I like it? No, I still hate them. But I begrudgingly admit that this is why this language is probably good. Okay? And I think they also dovetail really nicely with pattern matching, because the way I like to unpack my options and results is with pattern matching, and I think the completing formulation is if let, which I don't use. Some things that are less initially helpful are string formatting, because even though we can format strings, it's going to be a while before we're going to be able to see what's in those strings, so good luck to us, right? And then there's also the ownership system, which we'll need once we start having memory objects. And that's cool because has anyone ever made you write your own malloc?
Yes.
You are currently doing that.
Yeah, it's awful, isn't it? Yeah. So you get to use the ownership system, which I like to refer as malloc for babies. Okay? Shout out babies. Should we do a whoop whoop for babies too? Okay.
No.
All right. That's on you if you hate babies. Okay. They've never done anything wrong. They're the only innocent humans, right? You turn 12 and you're like stealing cookies from the cookie jar, right? But you're blameless before God for like a couple months.
Original sin?
Yeah, whatever. That's not until you become like fully human.
This is a heresy.
That's true. Okay. Quote the blog. It's based on the blog OS. These features make it possible to write a kernel in a very expressive, high-level way without worrying about undefined behavior or memory safety. That was not my impression of what happened, but it's nice that the Rust people think they solved this problem. And I think it's good that they're trying things, you know? So here's the things we keep. These things were all introduced in a prior lecture. So these were all the slides in the DRust. It was exactly this list. And now we enumerate the necessary steps to create a freestanding Rust binary. We actually don't get all the way through today because I wasn't all the way through and I was like, this is way too much content for today. And we're going to explain why the steps are needed at each stage. Okay, so the first thing we're going to need is no std. Do people say STD, standard, or stood?
Standard.
Okay. They say no standard? That sounds like you're like roasting your friend's dating choices. Like, oh, no standards. Okay. Which is true for some of my friends. Okay, by default, all Rust crates link the standard library. Okay, so we love Rust, right?
Yeah.
It's pretty okay. And we can tell this links the standard library, well, first of all, because there it is right there. Okay, this was a pretty good example. But also, like, println came from somewhere. Okay, if you say standard, you definitely say println, not println, right? Okay, and I always say println, so I should keep saying std. Okay, so we have std mem transmute. Okay, so this obviously has standard library in it. So how are we going to get rid of our standard library stuff? The other thing is that I guess Rust relies on a bunch of C stuff, which makes sense because C is awesome and cool. So there's some things in libc, the famous one being glibc. to just like introduce this idea a little bit, at least in Linux world, there's the kernel, and then there's like GNU core utils, which is like all of the stuff that actually works on your computer, like a command line or like any executables at all, right? So cat, I think, is core utils. Remember when I made you look up WC? And it's like, oh, this is GNU. This is not actually part of Linux. This is something that sits on top of Linux. So there's different implementations of libc. One of them is glibc, which is GNU libc. And that stuff is like so close to the operating system, it almost doesn't make the difference. I think, to me, like when I was first learning what operating systems were, I didn't perceive there being a distinction here at all. Now, slightly more mature, I perceive the operating system being the thing that works with hardware, and software on top of it as being utilities, right? But there's a lot of stuff that looks like an OS that isn't, right? Okay, so we're going to write an operating system. We can't use OS-dependent libraries. That would be recursive, which is awesome, but not in this case. So we're going to turn off the standard library with the no-stud attribute. And I provide links to the standard library, which is right here, and the no-stud attribute. Oh, this is outdated? I don't think I care. Okay. Okay, so you all know my ancient nemesis, cargo. My least favorite thing, right? That's not true. My least favorite thing is objects. Is that true? Probably. Okay, so we're going to start creating the beginnings of an operating system using cargo. And we're going to introduce two wrinkles right at the beginning. We're going to add the bin flag. Huh? Look, the guide told me we're adding the bin flag, okay? Take it up with OS Phil. Or Phil Oserman or whatever. Who is it? OS Phil. Phil Opperman. Philip Opperman. Okay. There, see? Ground truth, right there. Okay. All right. Well, I'm also pretty sure you don't need this at all. So, I don't think you need either of these things, and to prove it, I'm not going to use them. So I'm gonna cargo new, and okay. So, I called mine Osiris, which I think is so cool. But I took out the last I. So it kind of looks like Osiris, right? Because it's an operating system in Rust, right? This is very cool, right? I feel like you're not all appreciating how cool this is. Yeah, right. Thank you. Okay. So I created what am I doing? I always give these net numbers. So today is day 30. So I'm going to cargo new 30 name. I don't like VCSs, right? Yeah, and I don't think I need that other stuff. Cool. So here we have it. I bet this works. I'm pretty sure it does, but it probably won't in the future. I think that's for backwards compatibility. Okay. So, right. I'm going to assume throughout the course of the rest of this term, you're just going to have a bunch of different versions of OS kernels floating around, separated by numbers. Because I don't want to teach git branch. And also interacting with git branch with scripts is like a little bit more annoying. So if you use git branch, I will acknowledge that you're like good at computer or whatever, so you can use git branch if you want. But I'm cutting you loose. You're on your own. Why is that? Git branch, that's a software topic. I don't need to teach that stuff as a systems class. So you don't have to name your OS Osiris, but look at this art, right? This is what Osiris looks like. Apparently, Osiris is maybe the god of death, which is extremely metal, right? Right. This is very cool. And also, if you look them up, there's like this really, really not cool. No, stop. There's this, like, this is maybe the dumbest thing I've ever seen. And so I think we should. What does that box mean? In like northern Mexico? It's like clipping parts of Alaska and Maine.
Is it trying to include all of America? It's got Hawaii.
Oh, it's the company.
So anyways, these people seem terrible.
We should call them.
Oh, should we? Okay. Anyways. Yeah. I don't know. Cool. So, right. So what did we do? We did something. Wait, no, I already ran this. Okay. We're going to reset it real quick. Where's the command? Okay. Okay, so this is what things look like initially. I have a cargo toml, and I have a circ with a main ris. Okay? All right, and so what are we going to do with that? I think I've talked a little bit about cargo toml, but it's going to come up again, so I have to tell you what's in there. It's in Thomas Obvious Markup Language, I think.
Yeah, minimal.
Minimal. Tom's Obvious Minimal Language?
I'm pretty sure the Rust book says minimal, but maybe
The Rust book says minimal.
is it minimal?
Rust book, toml.
That is what it is.
We got to see this.
Weird.
Wait.
Oh, I'm not smart enough to Google this.
Is it actually?
But post it in Discord
Okay.
if you can find it. That sounds awesome. Okay.
I thought it was markup.
Well, the Rust book might be wrong, and then no. Oh,
Oh my god.
oh,
Oh my god.
go. Okay, Tom's Obvious Minimal Language.
We should get
Normal markup language.
You'll get an A. Okay. Oh, I'm getting very warm. Is it hot in here?
Yes.
Okay. Okay. So there's stuff in here. There's the crate name.
Originally Tom's own markup language, but then they changed it.
I don't respect change. Wait. Do not clip that. I respect change. Okay. I'm going to say one thing. Change we can't believe in. Okay, moving on. Okay, so we have a cargo toml. We have a circ main. After cargo build, we can find the compiled Osiris documentary in the target debug subfolder. You don't believe me? Here we go. All right, I'm going to cargo build. Okay. I'm going to cargo beak. I forgot to look around to see if Indy was in the room before typing out build. Okay. And then look at all of this garbage. Imagine a good Rust compiler, right? But anyways, here's this. Notice it's in green. Green means go, so we can run that. Target debug Cyrus. Hey, hello world. Yeah, that was fun, right? Okay, we're all having fun. Okay. Technically, no one can stop you from using cargo run or even cargo run release, but someone should be able to. And this is the cool way to run binaries. Sorry, no, I called it a binary. They're trying to get to me. Executables. Okay. Let's go ahead and slap a no stud in there and see what happens. And we're also going to change the text to bow down before the god of death because I think it's cooler to say that, right? Sometimes you just have to do things because they're cool, right? This isn't at all like try hard or cringe inducing, okay? So write that down. Okay, so we have a print statement. We have no stud. This is mainers. Let's go ahead and hit a cargo build real quick, and I bet this will work on our first try, okay? Oh no! Oh, what happened? The macro println is not available in this scope because println is part of stud. Is it unintelligible when I shorten the names? Println is part of standard, okay? And there's some other errors too that I bet will go away when we fix the first one, unless they don't. So how are we going to do this? So we got some errors. That's okay. Let's look at this error. We can't print without an OS. Of course we can't print without an OS. Why would we be able to print without an OS? We print by throwing bits over the bus. And the bit to bus people are the OS people, and that's supposed to be us. So there's no one to throw the bits over the bus, right? So what do we got to do? We got to get rid of println, okay? So that means we can no longer print things. Here is a comment. I hope it is clear how it is character building for me to assign you to create some code where you can't print anything out while it's running. Isn't that awesome? Like, this is my gift to you. Some of you are looking vaguely like perturbed by this, but this is actually cool. You should not be debugging your code. You should just write it correctly the first time. Okay, so let's go ahead and let's fix this up. That's probably fine, right? Wait, oh, I forgot to check if Indy was here. So we do Shift-ZZ, I think, right? It's really exhausting having people in your class. Okay. I bet this will work now. So let's go ahead and I'm gonna, well, let's look at it first to make sure we changed it. Okay. All right. Okay. So I don't see any print lens in there. All right. So there probably won't be any errors now. So I'm gonna go ahead and rip a cargo build just real quick. Oh no! Oh, there's still errors. Do you see this? Look at this. I need to write a panic handler function. And unwinding panics are not supported without stood. Standard. Yeah. Okay. So someone has to write a panic handler. And I don't know how to do that, but fortunately I found this blog online about how to write panic handlers. And so, not to worry, we got this error, but, okay. Here's how to do that. The panic handler attribute defines the function that the compiler should invoke when a panic occurs. Stood has a panic handler, which is why you've never had to do this before. But perhaps you've seen, I don't know if you've ever seen like this anywhere. Oh no, it's a panic. So that's something you can write. We'll just demonstrate this. Okay, so we can run this. Wait, it didn't panic?
You just built it.
Oh, I only built it. Okay, not to worry, I have a plan. Target, debug. There you go. Oh, it's a panic. It panicked, right? Ah! Okay. Is this how we do no stood? I feel like there's a.
Exclamation mark makes it an inner attribute, so it applies to the file instead of like the block below it.
So this is good?
Yeah.
Okay. All right. So we need to write a panic handler. No problem. I have an ingenious plan. I'm going to plagiarize. Okay. So I should just copy this naively, right? Because there's no way I'm going to remember all of these things. Okay. I'm just going to grab this. Oh, where do I want to put this? Probably in here somewhere. Okay. So what's this do? We have a panic handler. It's going to receive some argument. It has to receive this argument because of how the Rust language is set up, so it's going to receive the info argument. We are prepending info with an underscore to show that we're not going to use info ever, which is going to prevent us from getting an unused variable warning. I think we can turn that off and it's fine. What is that? Help! If this is intentional, prefix it with an underscore. I should have put that in the slides. I didn't. It's fine. So then we have, what is this? We have a reference to what? A panic info. Where does panic info? Panic info lives in core panic. So it's a core language feature, which I guess is differentiated from a stood language feature. And I believe this is architecture specific. Okay, so we have some panic info. We instantly throw out the panic info, which we denote by throwing it an underscore in front of it. And then what type is this? This is bang or exclamation point type.
Never.
Yes, so this is a never type, which means never. It is what it sounds like, right? And this is called a diverging function because it never returns. How can we tell it never returns? Wow, wait, should I just throw a return here? I bet that's allowed. Dang it. Okay, we tried.
Technically, the return statement itself returns never, but when it's used in the context of a function, we'll return the. We'll return whatever's being returned, which is by default going to be void. I don't know if that will work, because in that case, that one might work. It shouldn't work. No, it should work.
This should work.
Yeah, that should work. 'Cause in this case, you can also tell that it will never actually reach return.
Oh, no, it doesn't work. There was a separate error.
Because you're never supposed to construct an
Because you
instance
can't
of the
do that,
never
yeah.
type, which you are doing right there. And
I-
the compiler will yell at you anytime you do that.
This is why compilers are stupid. They should let me write bad code. And then I should get to run the bad code and see what happens.
I think somebody somewhere managed to get.
Okay, so what is
I
this?
don't remember.
This is a panic. What does it do? It's an infinite loop. Why is it an infinite loop? Well, we can't do anything else. We can't print. We can't return. We can't exit. We can't phone a friend. We cannot. We can't go and collect $200. That's a good one. Monopoly. Yeah, get it? Because Rust is going to have a monopoly on systems code. Yeah. Okay. So yeah, we just loop forever. Could you put something else here? So here's something I wanted to put here, and I didn't know if I'd get in trouble for this. I kind of want to just panic.
Is that not?
So that's what I wanted to do.
It's just a warning though, right?
Well,
Like, I think that would work.
yeah, let's do it. This is much cooler. That's not what I meant to do. Wait, I don't know how to combine these.
You just put stop them.
Vertically?
Yeah.
That's allowed?
You want to change it to allow instead of a warn.
Yeah.
Yeah. Yeah, it's allowed. They're just compiler annotations.
Hell yeah. Okay, now that's cool. I think we can all agree that that's cool. Now I have to update these slides, though.
We don't need to do that right now.
Well, not in class. I have to do it instead of, like, eating dinner, which is the other thing I do, then update slides.
Can I multitask?
So I tried, and I eat these peanut butter sandwiches, and they require both hands to pilot. I was like covered in peanut butter. Okay, the panic info parameter contains, do we care? No, not at all. The function should never return. That's why we're calling it. Exclamation point. So if you're a coward and you're just following along with the tutorial, you have to put a loop there. But if you're cool as heck, you just write an infinite recursive loop, right? And I think we can all agree that that's way cooler. I'd never heard of or used these things, but it was clear why they should exist. Right, okay. So if you're in a language where everything has a type, you have to have types to deal with panics. So of course you have them. And so there's like other types that came up. So I think like your main C can return a termination type or something. Like there's sort of these like peripheral corner types that show up. Panic info is just the first one we've seen. When else would you use a diverging function? Any gamers? Yeah, so what if you have a gameplay loop? And what if the game is Dwarf Fortress and there's no way to ever end, right? So you have a diverging function in your main gameplay loop because it doesn't return ever, right? I bet it works now. Let's check. We just checked, but oh no! Oh, we've bamboozled ourselves. Unwinding panics are not supported without std. But that's okay because we are big brain geniuses and we can read the next couple lines. Using nightly cargo. Do I use nightly cargo? No! Nightly cargo is for people that work too hard. So we're going to say, since the core library is usually precompiled with panic equals unwind, try rebuilding your crate with panic equal abort. Okay, that's exactly what it says. It says don't do that, but we're going to do it. Okay?
It says do it and it might not work.
So all we have to do then is we have to recognize what this syntax looks like, which is that is a key with an equal sign with a string value. And we've seen those before because they're in Tom's obvious minimal language, right? So all we have to do is just slap a little panic equals abort in here somewhere, okay? Okay, so fun facts. Panic abort, fun fact, back when I was an operating system engineer / rocket scientist, My first launch was PA1 for pad abort 1. So fun use of the term abort. They blew up a rocket on the launch pad to make sure it was safe for humans. And I guess it was. So like the little part that would have humans in it safely got out of the blast radius. And this is it blasting off. So in real life, I guess this is real life. In a live launch scenario, this is where you would put the astronauts, right? And astronauts are relatively expensive because they have families that can sue you if you kill them. So you try and make sure you keep them alive. I think there's like other reasons to keep them alive, but that's the reason I remember. Also, some of you may be aware that there is something in the United States called politics. I don't know if you've ever heard of this. So the use of the term abort, which in some nation states is a hot-button political issue, has come up from time to time in the discourse. Here's an article from 2018. In an early version of the GNU glibc, which I just introduced, there was something about aborting a program, and someone put something in here that said, proposed federal censorship regulations may prevent us from giving you information about the possibility of calling this function. Anyways, someone tried to take this out, and Richard Stallman, who no one knew was still alive or reading his email, told them they weren't allowed to take the joke out and had to leave it in, and said, GNU is not a purely technical project because a lot of the early open source software people regarded open source software as, among other things, a political project. And usually that means they were either communists or libertarians, and I don't know how those people are the ones that got along. But both communists and libertarians don't think you should regulate either speech or abortion. So, fun fact. Quote Stallman, I don't know, you should know these things. All right, so back to Rust. Now that we've learned about the GNU project's political stance and NASA, and you can both oppose fascism and then make sure you don't accidentally look up who founded NASA or who made Pad Abort 1 test. And then you just move on quickly and you abort programs in Rust. Okay, all right, so here's, let's abort some programs in Rust. Geniuses will recognize panic equal abort syntax, no problem, okay. So let's toss our panic equal abort syntax in our Tom's obvious minimal language. Don't tell me what to do, I'm an adult. Okay. I don't know why they let Jimmy teach this class. Okay.
Referring to yourself.
Kind of. I sort of felt like a victim in the whole process. So, you're all students, and I care about you all a lot, right? And so every once in a while, one of you will be like, hey, you should teach a class on X. And then I do it. And Jimmy did that to me once. And now I'm teaching operating systems. This is a lot of work for me, right? And it's probably a lot of work for all of you, too. So I think, okay, so Jimmy's gone right now. There's more of us than there are Jimmy, right? So we can probably overpower Jimmy and teach whatever we want in this class, right? Right? Okay. And I got the Malik assignment, which I thought was really cool, right? So, maybe there's other cool assignments we could do. Okay. All right, so just think about it. Okay. Act natural when Jimmy comes back. Okay. Nominally, there are use cases for which unwinding is desirable. Undesirable, whatever. I just never really got into unwinding. If my program explodes, I can figure out why it's exploding for the most part. I don't care. So anyways, unwinding seems a little bit too much like easy mode for me. And by the time you're writing Rust, why are you doing things the easy way? The compiler's already telling you the answer. So anyways, Rust provides an option to abort on panic. And I guess this reduces the binary size, which I don't know a great way to test that. Yeah. Okay, we'll look at this binary. So I want L, right? Target debug thing called play. Okay, so it's that big, right? Okay, and then now I'm going to nvim cargo toml, and I don't really remember what I put in here. Profile.dev, and then I say panic equal abort. Okay. No, Indy's here. Okay, and so then I cargo build. And it's the same size?
No, it might have been a relative change, because I think the standard library and whatnot.
It's because
It is smaller.
It is
Right. That number is bigger than this one.
Yeah.
How big is like the no standard right here? Or I guess we didn't build anything yet, did we?
You're also doing a debug build.
Okay, we'll do release. Okay.
You can just say opt level equals whatever in dev too if you want.
What?
You just change the opt level and whether symbols show up and provide that
Well,
too.
the dev is still gonna be.
Lots of people do optimizations in dev so that like debugging it.
But like, there's no reason to do it here, I'm saying.
Yeah.
Is it release profile? Is that what it's called?
Yeah.
I do optimizations in dev.
Oh no, I had to build it before I did that. Oh, that's okay. We'll build it. Well, this is what we have to check. Okay, and I think it's called release. Why'd I run it? Okay. What?
-L, not A.
I know that. Okay.
Bigger.
And then
No,
we're
that's smaller. That's
Okay.
a million and that's
we're,
100,000.
we're not done yet. This is it without symbols. Okay, right? Is everyone following what we're doing? That's a yes.
Smaller, because of the debug symbol?
Okay, we're gonna find
Whole
out.
video about making Hello World as small as possible. Discord. Did no one watch it?
No, we don't watch those videos. Oh, I need to cargo build again. Wait, did I cargo build released, right? Yeah. Okay. That's
Slightly bigger.
that's bigger. Okay, so hit fact check. Complete lies.
Well, it says considerably, but maybe it only means considerably in the context of no standard. I don't know.
I guess we can't really test it because we're not able to compile it.
Is it dynamically linked?
What?
Is lib and when dynamically linked?
I don't
when the
know.
program is run? If that's the case, then it won't show up in the binary size at all. In either case.
Okay, look, this is a quote from someone who nominally. So you sent me this blog.
Yeah.
Okay.
How could we? You have a.
Yeah.
So this is just not true. Now it may be true under certain conditions, but we're unable to determine the conditions, right?
Well, we're assuming the condition, yeah. Just you know.
Because we're very close to these conditions.
But we can't compile it without the appending thing. Or unless you do the unstable.
Okay. Well, at least we can build now. Wait, no, we didn't even update our cargo. Okay, okay. Not what I meant to do. What am I supposed to put in here? This stuff.
Yep.
Oh, I could have just grabbed the whole file. Ugh. Okay. Denny's here. Double Z. Okay. Now it'll work. Oh no! Oh, it still doesn't work, folks. Folks, we're cooked. We're like running out of minutes. Okay, that's okay. We're smart, right? Wait a minute. Okay, I'm gonna go on here. Okay, I bet it'll work now. Okay, see the problem? See the problem? Same problem, right? Same problem. So you're able to follow along. Our program is missing the start language item, which defines the entry point. What even is a language item, by the way? Like Rust is just like pulling things out of their like abstract model for computation. They're like, hey, have you heard of language items? No, I haven't. This is the first time they ever came up. Okay, I don't know what a language item is, but that's okay. I have an ingenious plan. This says, help, use no main to bypass the Rust generated entry point and declare a platform specific entry point yourself, usually with no mangle. Okay, I can do both of those things, right? I'm good and valid and worthy. So let's do let's hit a good, valid, worthy angle. Okay, so we're also going to add no main. When we add no main, we also don't need this, but we might as well hang on to it. I think we need something named start. And then we also need to hit a no mangle here. Oh, and no mangle's unsafe, right? So do I have to say?
It depends on the addition, but it's best to include it.
Is this how I include it?
Yeah.
Okay. It depends on the addition, but it's best to include it. Jimmy. Okay. I bet this will work now. Does anyone else think it's going to work now? Because I am 100% sure it's going to work. So I'm going to look like a fool. I'm going to be played for like a fiddle. We were pretty close. Wait, actually, this is much closer than I thought we'd get. Am I allowed to just call it start? I did think it had to be underscore start.
I did too.
Well, we haven't actually compiled it yet. But, okay. How many minutes do we have left?
4.
Wait, it's like, what's happening over here? That's crazy. Okay, so I was correct that perhaps we overcooked it today. We're going to follow up on this in the lab, and in the lab, your job is going to be finishing getting a binary working without std or anything else. I'm assuming you've been following along today, and you'll be pretty close. There's basically a Rust up step, and then there's some like theoretical content. My plan is then for the homework to be making you do this on RISC-V with QEMU, which might be crazy, but I'm going to try and get that working quickly, and I think it'll be really cool. I would really like you to have QEMU and RISC-V on your resume, and this is the place it fits in. I think that's all for today. We're on which slide did we get stuck on? 56. Okay, so I'll refactor this slightly, and I'll come up with something that vaguely makes sense for Wednesday. Cool. Thank you all. Have a good day.